Okay, so let's restart with the second talk of this session. So, Baldi will tell us about the Hodge Locus.
Well, thanks for the introduction, and let me thank the organizers and Jacob for the invitation, and also the IAS for hosting me for the year. It has been amazing so far. And indeed, yeah, that was the title I proposed, but since Elena has already given a talk on the Hodge Locus, I will give you also a subtitle. The subtitle is Please do type intersections. And this will be based on a joint work also in progress with David Urbanic. But before I get to this more recent work, I wanted to give something about the abstract setting that I will work with, even if it's similar to what was already discussed. And if you cannot see what I write, please tell me. Stop. So the abstract setting is very similar indeed. We start with, well, luckily we also have the same, almost the same notation. So we'll also work with SV, smooth quasi-projective variety over C, as before. And V, again, Z VHS. And so in the notation, I'm hiding the fact that it's polarized and pure. And I will tell you something later about the mixed case as well in a moment. But yeah, that's just to fix the abstract setting we will work with. Let me give you an example. So my definition of the Hodge locus that we get there in a moment is slightly different. And also the motivations are somehow slightly different, but again, it is a realm of period maps and period domains, and we will get there. Yeah. So let me just give you an example. So fix ND in n bigger or equal than 2. And we consider UND inside just the H0 Pn plus 1 C OD, parameterizing smooth hypersurfaces of degree D in Pn plus 1. So this space here is already a parameter space of hypersurfaces, but I need an open to consider smooth hypersurface. And over this space, we have a variation of constant. We have a V over UND, or a VHS, whose fiber at the point at our hypersurface X in UND is simply the HN X with Z coefficients, and I take primitive homology. And of course, I mean, you may be a bit upset because I took small numbers, but in some cases the VHS is not so interesting. It's a VHS. So that's one example to keep in mind. And the problem I'm interested in, and I've been interested in the last few years, is to understand I'll tell you what I mean by understand the locus as in C, such that the fiber of the Hodge structure Bs has special cycles, just to be in theme with the title of the conference. Special cycles.
You don't that's the product of
Yeah, I will. Now we will define, absolutely. Now we will define what I mean by special cycles, and then I will give you a precise definition of the Hodge, absolutely. But that will be crucial. So what do I mean by special cycles? I mean more Hodge classes in some tensorial construction of yes, then in the very general fiber, or in some tensorial construction, or in the respective tensorial construction of the very general fiber. Last tensorial construction. So what do you mean by Hodge classes? Maybe let me remind you, even if it was already said. So if H is a Hodge structure of weight 0, so let's say a rational Hodge structure of weight 0, a Hodge class is simply an element V in VQ, in HQ, such that when you see it, let's say V tensor 1 in V tensor C, in H tensor C, lies in the 0,0 part for this Hodge decomposition. Wonderful. Indeed, we need tensorial constructions because when we take, for example, if we were just talking about plane curves in this example, we would take the H1, these plane curves, and there's no Hodge cycle directly on the H1. We need to take, of course, like H1 tensor H1 and seek for Hodge classes in an even weight Hodge structure. So let me give you a better definition, but more formal. So given SV, we're interested in the Hodge locus SV. And indeed here I will put this tensorial construction. And we will adopt this Tarnakian perspective, and we will see that essentially fixing Hodge classes is the same as being fixed under an algebraic group given by this Tarnakian theory. So the Tarnakian group of the Hodge structure and of the VHS, and this set of points S in SC, such that the non-Forte group of VS is not equal to the non-Forte group of V. Not equal or not contained. So there's a canonical way to see this non-Forte group of VS inside the non-Forte group of a very general fiber, or there's a Tarnakian formalism for VHSs as well, and we can consider this. And this is just, so let me give you some, well, before I give you more examples, let's just take this is a subset of the complex numbers, nothing more at the moment. Let me give you just one example. That may be helpful, where we don't need much Hodge theory. So if you take D bigger or equal than 4 and you fix N equal to 2, in my example here, then this Hodge locus U to D, B, B the VHS from before, I mean, I dropped the indices, contains the so-called Noether-Lefschetz locus. So that's where the Noether-Lefschetz of degree D, that the Noether-Lefschetz terminology comes from, which is just the set of hypersurfaces X in P3, smooth, of degree D, where the map, the canonical map that we have from Picker group of P3 to Picker group of X is not an isomorphism. Yeah, so that's, and as you remark here, this is clearly an, I mean, it's really a countable union of algebraic subvarieties of U to D, because we are just working inside algebraic geometry and we are parameterizing the existence of some extra cycles. So that's the equivalent of saying being outside the Noether-Lefschetz locus means that the curves, every curve on your surface is a complete intersection of the surface and some other surface in P3.
Excuse me.
Yes.
I think there is a small issue with the definition.
Okay.
Because the non-Forte group of ES is always connected, but the non-Forte group, the Tarnakian group of the
That's right.
So
Yeah, I take the connected component. You're right. Yeah.
on the right, you should work.
Zero. Yeah, zero. I mean, I didn't define this precisely, but yeah, you're right. For example, if UVHS is isodriven, that's finite monomer. Absolutely. Yeah. Thanks. Okay, let me give you more remarks. So under the Hodge conjecture, and the condition. So if let's only speak of these, let me just speak of these Hodge locus, U and DV, for example. But any other geometric VHS would do the job. So under the Hodge conjecture, this Hodge locus is can be described in terms of what to say, Hilbert schemes or Chow varieties of effective cycles. And perhaps this was observed for the first time by Baldi in 79. And indeed, the theorem we saw before of the Catani gives in general, so for any B, the structure of a countable union of algebraic subvarieties of the base S to this Hodge locus here. So countable could mean finite. So countable in the sense that the cardinality of a subset of the natural numbers. The varieties of S to any Hodge locus. And in some sense, if V, let's say, was not geometric, this is not quite predicted by the Hodge conjecture, and this was done in 95. And that's somehow the starting point, but that doesn't quite solve the problem of understanding the Hodge locus. Of course, it's a very beautiful and very deep theorem, but it's not somehow the end point of this investigation. It's more like the starting point. Because if you want to prove the Hodge conjecture, in sense, you should look for an hypersurface, for example, in the Hodge locus. So where there are some extra Hodge cycles, some extra special cycle. Okay. So just to summarize this part of the theorem to relate it to this theme of the year, so for unlikely intersections, just maybe stated a little bit vaguely. So with Bruno Klingler and Emmanuel Ulmont, in 23, we proposed a conjecture, let's say, of Zilberfink / Bombieri-Masterzania type. For the qualitative behavior of the Hodge locus. And then we'll explain what it means in a moment, and then just say that and prove it. For HL of positive period dimension, so which we denoted by pos. So some components of the Hodge locus can be isolated points, other components, when you look at them in the period map, in the period domain, have positive dimension, and it turns out that essentially because of the fixed part theorem, understanding the components of the positive Hodge locus is much easier. So what it means is that, like, very quickly, so we work in this setting developed by Delini and Griffiths, and so we usually study V through its period map psi V inside a domain of this shape, and we can decompose the Hodge locus into the atypical part union the typical part, and the component y. So we can, this is really very much inspired from the case of Shimura varieties, and the component y inside the Hodge locus can be understood as essentially psi minus 1 b of dy mod gamma y. So this is the smallest sub-Manfortini domain of d mod gamma containing y, and the component of this intersection. So, and y in the Hodge locus is atypical simply if the codimension of y in S is strictly smaller than the codimension of dy in D. And otherwise it's typical, and the conjecture says that the atypical Hodge locus should be Zariski closed. There are only finitely many maximal atypical subvarieties, and the typical Hodge locus should be either empty or dense. And the goal of today, rather than explaining you this very general viewpoint of today, is to give an example of this philosophy in very concrete cases. And maybe the subtitle is how everybody could have invented this completed Zilber's-Pink philosophy. So we start from a very basic observation and build up from there.
What do you mean by H and positive? It means positive dimension in
the period domain. Thanks. So y in S is positive if dimension of psi of v y bigger than 0. And I can mean dimension in the complex analytic setting if I extend the period map a little bit before, or if I use this theorem saying that this is an algebraic variety, I can understand dimension in the algebraic set. But maybe the best thing to say is that pos just means that psi of y, psi v of y is not a point. So in this way, I can avoid speaking of dimensions. It can be tricky. So in this setting, the period map is not algebraic, and d mod gamma is not algebraic. And this is really the theory envisioned by Deligne and Griffiths. Okay, so let me go to the second part of the talk, and so to speak of these Bezout-type intersections. Maybe very briefly recall what I mean by a Bezout-type intersection. Everybody knows it. I start by drawing a picture. And maybe these kind of things were known long before Bezout, but okay, that's all we are called today. So let me, sorry, any remarks?
What's the definition of Bezout?
Yeah, I will give it exactly in this theorem. Yeah. So we take x and y inside Pn. Let me work over, well, I can work over any field K, but then I will work mostly over C. Two irreducible Zariski closed subvarieties. And if, so that's the first theorem, if dmax plus dy is bigger or equal than n, then x cap y is not empty. So what I call Bezout type is like when I'm in this range. So I care about Bezout type intersection when I have two subvarieties in an ambient space. That could be, maybe later on will be a manifold, but I call the Bezout type when dmax plus dy exceeds the dimension of the ambient space. So here in this Zilber-Pink business, we had this atypical, strictly very important. And I want to tell you how these kind of things. So the first theorem of Bezout is that first of all, x and y they intersect, And then there are like, maybe I will not write all of them. The second is that there's a degree formula if the intersection. So when they intersect, this intersection can be transverse or the subvarieties can meet properly. So one question is whether the dimension here of the intersection is the expected dimension. So dmx plus dy minus n, or whether it's bigger. If the intersection is of the expected dimension, there's a degree formula of this type. And if the intersection is not of the expected dimension, you can move for some g integer n integer n plus 1 c x cap gy can be made into a transfer into an expected intersection. Even if x and y they didn't have the expected dimension. Okay, so this is a bit far from Hodge theory, but there's one case that will bring us closer to Hodge setting, and it's given by, well, semi-abelian varieties, or let me start just with abelian varieties, and then I will move to Shimura varieties, and then if there's time, to variation of Hodge structures.
No, because the Bouzou you have for abelian, for simple abelian.
Yeah, exactly, I'm getting that. That's the next statement. Yeah. So theorem. So the first example done by Bard in 68 for the case k equal to c. I did much more is known nowadays. So just the work of the Bard. Azad. And very recently also the Bar and Muller. Or any case. But I mean, I will work in this setting. You know. So the following is the statement is the following. Let A be an absolutely simple. So let me just work over C. So let A be a simple abelian variety. We take, we're interested in this Bezout type intersection. We take x and y in A, such that dmx plus dy is bigger or equal than dma. Then x intersects y. So that's the theorem. And yeah, I'm very happy that people already knew it, but somehow I have to admit that I discovered it fairly recently. And when I saw it, I mean, it immediately looked like one of these developing problems, but it was not fully clear how. And then this inspired this recent work that we are currently writing with David. So I can give you the first improvement that's along those lines here. And then I will give you a better statement. Yeah, so the first one, so we take, again, we take x and y, the same setting, so x and y in this range here. And the statement is that for all but finitely many n, in the endomorphism of A, x cap ny has the expected dimension. That's the first part of the statement. And and furthermore, moreover, the union along all these n, let's say big enough, of x cap ny. So we take this union and we take it to make it meaningful. I mean, of course, y can be equal to n times x, and in that case, this theorem is not there. I mean, you need to change n, but then for the next statement I'm about to state, it's important. So I want to take the union of x cap ny, and I take the union of the components with the expected dimension. So that's why I denote by to the e, and I claim that this union is dense is dense in X analytic topology. And I will give you, maybe this is not so impressive, but I will give you a more defined statement. But first of all, I want to explain how, so maybe I define this, the U. In all axes. And why? Of expected integers.
Is n an integer or an arbitrary element?
Yeah, that's a very good question. So yeah, both, but let me just, I mean, when I wrote this, I really meant endomorphism. But in fact, there's no harm into replacing, I don't know who asked the question, but yeah, there's no harm into replacing Z by the full endomorphism algebra. Yeah, we prove it in that case. And you will see why in a moment. But just for the sake of giving the simplest statement, because I want to explain you the proof, let me just take Z. Thanks. For the,
So you reprove Moonen?
no, in fact,
You use it?
I use it, but in some sense, in the strategy, we can reprove it in the weak sense. And also simple is not so important. So there are formulations also for non-simple abelian varieties, but under the suitable statement, of course,
Yeah.
I don't want to take A cross A cross B. And so you can force the intersections, but for some n. So this statement will always be true, but you don't know whether like every single intersection will happen. So we can control only the transverse intersections, and we cannot say anything about the other ones. So if even X was inside Y, in some sense, in this proof, you will not notice it, and you will not prove that the intersection of X and Y is non-empty. But you will prove that this intersection, yeah. And this point, when we give a statement for Shimura varieties, will be much more important, because we don't have this bar theorem for Shimura varieties, but we will prove a version of that. When we replace the multiplication by n by the translate by a naked translate. But let me explain.
Improving in analytic topology the density.
Yeah, that's right.
And you get some equidistribution.
That's also true. Yeah, yeah, that's actually
But did you, I apologize to say that, did you talk to Ben Moonen or not?
no, not really, not
Because,
yet.
I heard, I listened to a lecture of Ben like a month ago in Stockholm.
Mhm.
And Richard Pick was there.
Yeah.
And immediately we asked. Yeah.
We didn't.
Yeah.
But in fact, I mean, I can tell you the story. We saw the paper of the bar and Moonen when we arrived here at the IAS, and then we immediately realized this, and then we started working on this type of things.
But maybe to be, yeah,
No,
so you
sorry.
do, it's an information.
No, thanks for pointing out. Yeah.
So when you say for any K, maybe you said this and I missed it, you mean for any characteristic, basically? Or
Any field K of any characteristic,
not
not necessarily, no, not necessarily
necessarily.
algebraic, but in that case, I need to assume that A is absolutely simple.
but it might not have points, but the intersections you count points over an algebraic closure, is that right?
That's right.
Okay.
It's like, I mean, it's the same state in Bezout. Bezout at the end boils down to something in commutative algebra, and Bezout is for any K, it's the same.
No, but then it's essentially algebraic closed, right? Because you can just base change that.
Yeah, I agree. Yeah, but just to clarify, the bar plus the bar Moonen is really for any K of, I mean, the main crux is to do any characteristic. And indeed, the proof becomes much harder in characteristic P. So in characteristic 0.
And you have to, yes.
Yeah, so these three people were more interested in characteristic 0.
Yes.
From here on, it becomes much more difficult than its characteristic. But indeed, I will explain, this is very simple.
Sorry, Greg, can I ask a question?
Yes, please.
You still have the condition that dim x plus dim y is bigger than equal to dim a in your theorem?
Say it again, sorry?
You have the dimension condition on your.
Yeah, absolutely. Yeah. Sorry, I didn't repeat it, but in the same setting. So A simple, thanks. A over C simple. X and Y, let me say, in the Bezout range. And yeah, in general, I will, in this talk, I will always be interested in this range. And you will see that it's a mixture. So let me give you a sketch of the proof. So you just consider you just consider X cross Y inside A cross A. And notice that X cross Y is what we call generic in some sense. It's not contained. I mean, let me also assume that both X and Y have positive dimension, otherwise I'm lying a little bit. X and Y is not contained in any translator for some sub-abelian variety of A cross A. And this intersection I'm investigating here is really about, so let me call it gamma n inside A cross A, the graph of the multiplication by n. And what I'm interested in is in the projection to X of X cap Y cap gamma n. So I'm interested in these intersections. And before I gave you a very general Zilberpin conjecture, but in fact it can be specialized to the case of abelian varieties. At least, I mean, I was lying a little bit, I didn't give you the statements for mixed VHSs, but if you formulate it for mixed VHSs, it implies something for abelian varieties that was already done by Habeger and Pila, maybe in 2016. And so the point is here, if this intersection is not of the expected dimension, it means it's bigger in dimension. It's bigger in dimension, so if this intersection has bigger dimension than expected, then it is an atypical intersection of positive dimension, of positive period dimension, of positive dimension. And therefore, we can use the this so-called geometric Zilberpin conjecture. Well, theorem for subvarieties of A cross A. This is actually was done first by Habeger and Pila, 2016. And then once you have this viewpoint, I mean, there's also these theorems about the density of the Hodge locus that we did in Hodge theory, and they can be adapted to prove that his. So let me just finish. So this theorem here will tell you that this atypical positive dimensional intersection will be contained in a finite union of atypical intersections. So, and you can check the atypical intersection that this theorem is producing. They have to be again graphs of the multiplication by some integers or some endomorphism. So it's saying that all this union in the atypical components lies in some finitely many graphs, and that's why you have to exclude some of these ends, and then essentially you are done, and the density follows. Yes, okay. But the equidistribution is more delicate, but I will go back to this. But what I wanted to advertise here is just that from a Bezout type of intersection, if we work in the product, we went back to this kind of unlikely intersection problems, and we had both something that looked potentially typical, so because this guy has dimension dMA, this guy has dimension exceeding dMA, and we're in a dMA plus dMA dimensional space. But then the atypical intersection, so the excess in dimension, it's related to some sort of Zilberpin conjecture. And my slogan is that I wanted to convince you that the positive dimensional Zilberpin conjecture is kind of doing already something for you. And here is the only case you care about. You don't care about the more subtle intersection problems. So let me give you a better statement than theorem one, so a more precise one, and then I will move to Shimura varieties, which is maybe more interesting. Unless you have any comments.
I'm looking for the Hodge Locus.
Yeah, we get there. But you can already kind of see the proof. Yeah. That's right. Okay, let me give you theorem 1 plus. And it's the following. Now we take AL. So yeah, maybe a remark. What I liked about this problem is that it made us think about certain improvements on this Hodge Locus business, and then we were kind of motivated by this to push the general Hodge Locus theory to a new setting. So yeah, so we take a principally polarized abelian variety, and we take simple. And I hope the sketch of the proof answers also Daniel's question. So these graphs here are this one special subvarieties, and there's no difference if you took the graph of some arbitrary random. Unless A is simple, and then you have to. Unless A is not simple, in which case you have to pay attention. So you take xy in A, again in the Bézier range, so d max plus dim y bigger or equal than dim A. And so the refinement of the first part is the following. So there exists an n, there exists a constant c, depending only on the degree of x, the degree of y, and maybe I will not have time to explain it, but also only on degree of L and dimension of A. Such that for all lambda in end A, so now I give you the more general statement, of degree bigger than C, every reducible component of x cap lambda y has the expected dimension and the furthermore part, the moreover part, is the following, and it's related to Peter's question. So for any sequence now, lambda I in end of degree, well, of degree, of unbounded degree and bigger than C. In fact, you just need to take you don't need to take the union of all intersections because there's some equidistribution behind the scenes. In fact, the union of x cap lambda I y, or I number here, well, you don't need this expected, dense in x. So let me just give you two remarks and then I move to the case of Shimura varieties.
But what is lambda I?
So, yeah, sorry. I take any sequence lambda I of endomorphism A, so I change the notation to give you the more general endomorphism. I take any sequence of such endomorphism with degree going to infinity and bigger than the constant given before. And then I take the union of these typical intersections with this Bézier type of intersection only along this sequence lambda I. And in fact, this one will be dense. Before it was just the full union, but you couldn't specify a certain sequence. And this
What is this doc L? Because you say principally polarized.
yeah.
So you allow polarization of any degree?
Well, I fix also the degree of L.
What is it?
Well,
It's principally polarized.
yeah, sorry. No, you're
Well,
right.
you can also just erase principally polarized.
Yeah, that's right. Yes, you're right. Good point. Sorry. Yeah, I could. That's right. Thanks. Good catch.
Can I ask a silly question?
Yes, please.
Why do you have bigger than C if the degree is unbounded anyways? What, am I
Well-
missing something?
Well, I mean, yeah. No, you're right.
Sorry.
No, good point.
I want to make sure.
No, but I mean, to have like, I mean, I could have erased the typical and then I want the deep C, but then I put it nevertheless. So you're right. And the proof is similar, but now, so what's the improvement here? To make this intersection kind of uniform as you vary x and y, it comes from some sort of improvement on this Abegger-Pilar theorem, where we do essentially a uniform geometric Zilberpink in families. And you can do it in families only of degree of x and y, so you stay small in A. You can also vary the abelian variety and it becomes a geometric Zilberpink at the level of the universal abelian scheme over AG. And that's based on an earlier, so this is some sort of based on our proof of geometric Zilberpink for mixed VHSs. That we did in 24. And yeah. Okay, so rather than getting you there, but I mean, what I wanted to say is that this theorem, this Bezout theorem, motivates us some sort of refinement, like trying to make the geometric Zilberpink conjecture uniform, and we will see this again in the Hodge structures, in variation of Hodge structure setting, consider as doing some Hodge locus and lambda I. So let me give you now the picture inside the Shimura variety. And then what happens also for more general VHS. Maybe 3. So maybe, and I will also give you some applications. So maybe what I mean, so let me just recall the setting. So now I denote S by d mod gamma. I don't quite work with Shimura varieties, but so it will be d mod gamma, a locally symmetric variety. Where gamma is an arithmetic and irreducible lattice subgroup. But irreducible is important because I want to some sort of simplicity condition in analogy to the case of abelian varieties. Some sort of simpler condition. So for example, well, maybe with some level structure. Otherwise, it's more like Shimura style. So I take also gamma. Well, just to be precise, don't shoot. Okay. So the problem, so we are interested, we look at x, y in S such that, well, dmax plus dy exceeds dms. That's the first thing. And the second thing is that x and y are Hodge generic in S. So what does Hodge generic mean? It means that either they're full monodromy. So if you look at the monodromy representation, you get the same connected component of the identity of the monodromy of S, or in this case, that they are not contained in any sub-Shimura variety, Laplace of a sub-Shimura variety. And so in the abelian variety case, is not this was not appearing, but it was automatic. But in fact, the problem here is that S itself, and even if it's simple, it could contain sub-Shimura varieties which are a product, and I don't want to work with X, which is one sub-Shimura variety across a fiber, and Y is the same sub-Shimura variety across another fiber. So I want to be away from this.
Sorry, Greg,
Yes,
would your hypothesis about dmx plus dy bigger than dms and S being simple rule that out?
say it again, sorry. So dmax was, yeah,
You're assuming that S is simple,
yeah,
and you assume that dmx plus dy is bigger than equal to dms.
yeah.
So won't that rule that setting out?
You mean it's no, why taking AG? You take AG minus 1 cross AG minus 1, and I don't want to take I don't want to get a point cross AG minus 1 as an X, and a second point cross AG minus 1 as well. But in this case, AG minus 1 cross a point has dimension such that if you double its dimension exceeds the dimension of AG.
You see kind of two definitions of generic about monodromy, about searching more variety. Is that the same? or-
Yeah, so, yeah. But just because the lattice is simple, so I know that the monodromy is a normal subgroup of, well, okay, no, it's not the same because you could take as X a Hodge generic, a point with Mumford Tate equal to G, and that point has no monodromy whatsoever. It's not, I apologize, it's not equivalent. But if X has positive dimension, then they are equivalent because I know that the monodromy subgroup is a normal subgroup of G, and they take G in the derived subgroup of G, and I'm taking G as a simple group. So the only normal subgroups can be G of the trivial subgroup itself. And if I exclude the trivial subgroup, then the monodromy has to be G. And this is why it's explained in an article of Ivan Drek, and it's based on the semi-simplicity theorem for the monodromy and the fixed part theorem. Yeah, so maybe in general, you ask me monodromy, algebraic monodromy, the connected component of the algebraic monodromy. Yeah, exactly.
Okay.
The algebraic, yeah, you're right. The algebraic monodromy is a normal subgroup of the derived subgroup of the generic Mumford theorem. Yeah, just to relate the two definitions. But of course, if you give me 2 points, they are generic. They can be generic. Thanks. Okay, so what do you want to say? So, well, maybe the question, so that would be the true Bezout theorem of Barth in this setting. And again, as hinted before, we didn't answer it. Let's also assume for simplicity, say S is also compact. Just to avoid problems at infinity, is X cap Y non-empty. Well, we will not answer this question. I mean, it's not fully clear to me. Maybe sometimes yes, sometimes no. So I didn't think about this fully. Maybe someone has a counterexample on the spot, but okay. So we will go back to this question later. So the analog of the multiplication by n from A to A in this setting here is now an equicorrespondence. And indeed, in a moment, we will see that there's also some equidistribution here as well. And so, yeah, what's G here? G is not the same as here, of course. So G is in, well, let me say GQ plus, or maybe in the commensurator of gamma. And what's gamma G? So gamma G is just gamma sub G, gamma G minus 1. Yeah, so those are correspondences that dominates both factors, and so maybe it's more like the analog of the graph of the multiplication by n. In this setting is these things. And I should say that intersecting a curve with its AK translate or intersecting a curve with its own multiplication by n is a standard step in this kind of Manning-Mumford and Andre-Orth conjecture approaches. So we were kind of inspired by this. Even remove y from the game. Just take x, cut TGX, and you take x of half dimension. Okay, in the Bezout style, we kept x and y. So what's the theorem? But are there any questions on the setting?
Yeah, maybe
Yes, please.
once more.
Yeah,
Is that true? There are compact Shimura varieties of dimension 2. There are K3 surfaces, some. And what is your question about?
No, so I'm not sure. So maybe it could be possible that some K3 are Shimura varieties, but
not all. Yeah, sure.
but that's very rare, right?
Yeah.
So I
but,
mean, as a
that's-
compact Shimura variety, I'm thinking more you could take a product of 2 compact Shimura curves, or you can take these Boy quotients, like you can take these kind of things. So, I mean, when I put some level structure, usually I don't think Shimura varieties are simply connected objects. So I took gamma torsion free. So strictly speaking, in this setting here, so I'm not quite working with Shimura varieties indeed. So, but in some sense, it's a Hodge theoretic statement. So I'm not really thinking about K3, more something with gamma as a fundamental group. But in some setting, it could be that it's a K3 in some sense. That's also true. But
And this was my question.
Yeah.
Because you asked whether we have question on this case, but maybe there are no such X. I know what are the X of dimension 1 in a case 3, which is a Shimura surface, and which is generic Hodge with your terminology. What are they? Because that would be a good test.
yeah, I'm not sure in the K3 case. I'm not. So what's the group you're thinking?
I don't know.
What's the group? I mean, there are not many options. So for sure, well, but yeah, there might be a lot of compact factors. So for example, so let me maybe give you a remark in this sense. So there are compact Shimura surfaces associated to complex to PU12, and in that case, it's also maybe for PU12, it's also possible that there are no sub-Shimura varieties. So certain Shimura varieties have no sub-Shimura varieties at all.
But you don't have any two-dimensional example where you could test your question here? It's just.
Not yet. Maybe
Not yet, okay.
maybe by Christmas.
Okay.
Or maybe no, I don't know. Maybe no, but Christmas brings a lot of.
We do Christmas.
Christmas brings a lot of gifts. So.
We call it, what is that called? Seasons.
Season greetings.
Yeah.
So that's season gifts. Yeah. Or if someone has some ideas, I mean. Yeah. But let me tell you what we can prove. So in fact, so theorem 1. So let me be. So this is theorem 2. Well, no, maybe that's theorem 2. So for all G in GQ outside outside some bad locus, X cap TGY is non-empty and has the expected dimension. So meaning in X plus in Y times in S.
What do you mean by Hodge Locus?
Yeah, so bad locus is outside a strict algebraic subvariety Y inside G. Maybe W inside GC. So I don't want to be allowed peak points, and I will explain now where it comes. Yeah, and furthermore, yeah, let me give you also the second step.
It's somewhat different from the Abelian variety case, but only finite.
That's right, because in some sense, simple Shimura varieties, they have sub-Shimura varieties, whereas simple abelian varieties, they don't have abelian subvarieties, unless of dimension 0. That's right, somewhat. Moreover, for any, but this second part is more similar, so for any sequence, well, generic sequence. Generic meaning just it converges to generic point of GQ for the Zariski topology. The union along I of X up to G I Y of the expected dimension is dense in X. So the right analog of the previous statement is really to take generic sequences that converge to the generic form, that they don't accumulate, for example, to some subgroup of G. And it is, yeah, let me also, before I explain it, let me also give credit. So there's a special case that's also very similar to this strategy, proven by Taillou and Tolosan. Maybe in 23. They prove a special case of this result when Dmax is bigger or equal than 2 and S is equal to AG. But in fact, their theory here is really based on some sort of typical intersections, equidistribution of typical intersections. So they prove much more than just this result. Which, first of all, you need some equidistribution of EQ operators of special subvarieties that, at the end of the day, comes from Ratner as well. But to get their theory working beyond these cases, there's one thing to check that, in fact, some of the intersections are non-empty. Somehow, in their theory, there's this push-pull form that could be 0, and so that would be prevented. That could be, so they can prove if some of these intersections are non-empty, then they equidistribute and they also have the expected dimension. And in some sense, in this theorem too, the main crux is to get this typical intersection to be non-empty. And there was also the lens point from before. So how do you actually reprove this Blitzing theorem? So maybe if there are no questions.
I'm still confused about your Hodge Locus because you solely don't want V in gamma. So how do you exclude cells?
Yeah, that's maybe should be in GQ mod GZ. I need a sequence of elements. Yeah, you're right. I'm really working in the commensurator of gamma mod gamma. Yeah, you're absolutely right. Indeed, here I take care. In the second statement, I'm more precise and I take care of them. That's right. So let me show. So let me start with a more modest goal. In maybe 5 minutes, let me show something smaller. So find G in F. In respect to gamma mod gamma, such that y x capital Gy is non-empty. So that's somehow an important ingredient in the proof. So how do we find this? And this actually follows from, so we will use these actional results. So in this theory, I mean, I hope the moral here is that in this game, there's always a mixture of typical and atypical intersections. And indeed, there's this philosophy behind it. And I want to use a mix, I want to use an actional theorem in this setting, which were described yesterday, and in this generality, it's the one proved by Mock, Villa, and Zimmerman. And in fact, this idea, I mean, it's very similar, but it doesn't quite follow directly from, I mean, this idea was already employed into papers of heterogeneous Scanlon, as well as Khalifa and Urbani. And maybe I should also remark that in the geometric part of Zilber-Pink, a crucial statement is in fact this actional theorem, or maybe an actional theorem in families, and that's also what we use with David. Okay, so let me show you rather than. Let me show you this idea that I think is quite powerful. So again, you take x cross y in S cross S, and you remark that this one is once more a generic. And to have this assumption, you need dim x and dim y of positive dimension. Which are really not in the statement, but you can reuse in this case. So we'll be very quick. I hope it's clear. So we can take x, y in x cross S or generic point. And can also take x tilde, y tilde inside pi minus 1 d of x cross x, x cross y, inside d cross d, where pi is the uniformization method. And I can also decide, I can find G in GR, since G is left intransitively, such that y tilde is equal to GY, GX tilde, right? But I mean, maybe I should have called this element here that I'm seeking for Q, because I want it, of course, to be a rational element, not a real one. But first of all, I can find a real one, and so it will be an approximation from real numbers to complex numbers. I have 1 minute to conclude. You can take dg inside d cross d, somehow the universal covering of our Hecke correspondence, just the image of d twisted by our elements g. And the point is that dg cap pi minus 1 of x cross y is either typical or atypical in this sense. And if it's typical, we can deform it in the sense of differential geometry. And in a neighborhood of this G, we can find a rational element that's going to be again typical. And so we will win. And if it's atypical, we contradict a channel. Because x and y was all generic, x tilde and y tilde was all generic. And this is essentially the strategy already employed here. The only small difference is that there's always a problem working with products. And the thing to be added here is that the output of Akshanian theorems are again graphs of fake operators, because in D cross D there's nothing, and they know that X and Y are all generic in X and Y. So if you want this kind of, the missing input is some ghost type of observation. To control the output of function. And once more, the point is that atypical of positive dimension. Because we are once more in this range. So you have to use the assumptions dim x plus dim y exceeding dim s. So it was a bit quick, but I hope it showcases the link between typical and atypical conjectures, and at least one link between Akshanian and Hodge Locus. And I will stop here. Thanks.
Questions?
Once you have this density, can you then apply the arguments of Tayu and Todan, get the distribution?
Yeah, that's right. Yeah.
Okay, so you're right.
Yeah. Sorry. So, but in fact, it's even better. So that's so. Once you form these intersections here, and they are non-empty, you can prove they are dense by moving these things. You can prove that they are positive. You can prove they are typical, because otherwise you would contradict Zilberpink. But in fact, you can also avoid using the geometric Zilberpink and just say, once you have one intersection which is non-empty, this is enough as an input for the Tayu-Tolosan argument, and then they prove the equidistribution, and the equidistribution forces also the intersection to be of the expected dimension. But of course, with this Zilberpink, you can control more things. Maybe you can make the intersection transverse. You can control the Manforty group of the intersection. So if you dig into, it's there. But in some sense, just one cube is enough for their strategy to run. Yeah, so you're right. Yeah, absolutely. Thanks.
So are you familiar with what this conjecture in modern theory called existential algebraic closedness?
Yeah, I heard. Well, I wouldn't say familiar.
This is very similar to what you're doing. You're taking, let's say, for a simple abelian variety, you take the universal cover.
Yeah.
You intersect, so it's even in the product of Cn and A. You intersect with a variety where there is an expected intersection. Let's say you intersect something with dimension n. Then the conjecture says that, okay, if it's the correct dimension, there should be an intersection. In fact, the intersection should be Zariski dense. And
but this is given a subvariety of Cn cross A.
yeah. So for instance, for you could take A times A, and this multiplying by n that you do, you can encode it by, on the level of Cn, writing that this Cn is n times that Cn. And some of this, so for instance, for simple abelian varieties, I proved this conjecture, but I mean, it wouldn't give anything for your case because you need A times A. And actually, the conjecture is very interesting when it's not simple.
Okay. And are the techniques more similar?
Techniques are similar, and there are people. I think Aslanyan works
Yes, that's
on
right.
this,
Yeah.
and he
But
does,
I think also
and Turovic does in Galileo.
it was their motivation.
And
also.
I mean, they are kind of using geometric Zilbert pink in a way similar to you, and they have something called the blurring of the J function, which is a little bit similar to what you are doing. So just it's worth having a look.
No, of course. Yeah.
I think they also use Ratner for some case for the J function. So it's kind of reminiscent.
Yeah, but I think it's similar. I mean, many of these ideas were around. I mean, the way I see them are inspired by this conjecture. Either the atypical Hodge locus is Zariski closed, the typical one is either empty or dense. So we see all of these kind of things together, but of course, many people arrive to this conjecture from different directions. And I think this is, thanks a lot. I would certainly.
But of course, but I mean, the initial result that you mentioned by the back, that falls completely outside the scope of this thing, because they always rule out, this variety should be somehow outside the weakly special case. And I think the bar result for simple abelian varieties, that would be the weakly special case for them. So it does not follow even from the strong existential algebraic closeness, I think. But nevertheless.
And we will see the proof that the intersection is forced. So it's very simple. It can be.
But maybe you can show it. But I think it would not follow, I think, even from this full conjecture. Yeah.
No, but I want to say that, then after Barth's proof, other people came up with simplifications. So now the proof takes a paragraph, so you can read it and digest it. But when I read it, I was very impressed as well. Yeah, very much.
Okay, any other questions? Okay, so was there a...
Yeah, do you expect a p-adic density result?
You mean, say I take my Shimura variety, some sort of local Shimura variety with the p-adics, and I try to do the same.
Yeah, like density in the p-adic analytic topology, the same intersection.
I'm not sure, but there are statements of this channel that's maybe the main input with the views that works over the p-adic numbers as well. So here there's some transcendental arguments. So I would have to think.
But actually, does it depend? It's just differential field of characteristics.
Yeah, exactly.
Does it matter?
Yeah, exactly. No, there is a channel. No, there is a channel over any field of characteristic zero. Proven by James, his collaborator. Maybe Nathan Dogra noticed that. So a lot of the inputs are there. But then, of course, here there's some complex Hodge theory behind the scenes. So there's the other input is always the link between monodromy and Mumford-Tate groups. So I'm not sure how it works over the p-adics, but I don't want to say yes or no. Other people maybe have a better answer, better guess.
Okay, let's think the bigger.